Hello everyone, I'm Norman Wahlberger and welcome to 6. This is a course in pure mathematics meant for a very general audience with minimal mathematics prerequisites. So I'm going to introduce you to the wonderful world of pure mathematics. So last time we were talking about cycles and the 3-4 bridge, and I want to talk a little bit more about that and make a connection with some interesting geometry having to do with conics. Okay, so what we're investigating is actually quite elementary and combinatorial, and we're not actually motivated by anything in particular. We're just interested in exploring what we can find by fiddling around with some very basic building blocks, almost like Lego pieces. But as we do that, if we discover something that connects with something else, I want to point it out. That can be reassuring for us that we're in the good direction because we're making contact with something else that's interesting. That's what's going to be happening this time. So we're going to be talking about the relationship between 4 and 3 that we discussed last time. So if we start off with 4 points, say 1, 2, 3, 4 in the plane, so we're actually sort of thinking about some physical representation, then we had 3 associated 4 cycles that we could associate to this set of 4 points. Here are the four cycles, and associated to these 4 cycles are 3 meets. Okay, and in terms of a quadrangle, which is just a set of 4 nodes, 1, 4, 2, 3, let's say, then these meets have traditional names: 12.34, which represents this one; 13.24, which represents this one; and 14.23, which represents this one. So the way I've proceeded so far is the meets actually sort of refer to the points of intersections of these edges or lines. So today we want to augment this picture and connect a little bit with some geometry and actually bring conics in a very simple and elementary way into the story. Okay, so I want to now connect with some projective geometry, a very elementary kind of way. This is a beautiful and simple and natural kind of geometry in the plane, only consisting of points and lines, at least initially. So suppose that we start with a quadrangle, 1, 2, 3, 4, which we're going to visualize in the plane by 4 points. Say 1, 2, 3, 4, the 4 red points. And I want to show you the 3 meets that I showed you in the last slide, but now all together on the same picture. Okay? When we do that, we get 3 diagonal points and a corresponding diagonal triangle. So we get a very important construction that associates to a quadrangle consisting of 4 points, a triangle consisting of 3 points. All right, so this is a very strong example or a geometric illustration of this 3 to 4 bridge. So what do we do? So here are the original 4 points. And those 4 points determine 6 lines. The lines are like the edges: 1, 2, 2, 3, 3, 4, 1, 4, along with 2, 4, and 3, 4. So the 6 lines which are in blue here. So the name of this line, or this edge, would be 1, 2. The name of this line is 3, 4. And the place where 1, 2, and 3, 4 meet is this point here, which we could represent with this meet notation 1, 2, 3, 4. And let's call it A. Correspondingly, there's also the meet 1, 3, 2, 4, the meet of 1, 3, and 2, 4. So that's B, that's right there. And C, the meet of 1, 4, and 2, 3, that's up here. So the diagonal triangle is this triangle ABC, formed by these 3 diagonal points. So we start with this quadrangle of 4 points, and we get this diagonal triangle ABC. It's a very fundamental kind of construction in elementary projective geometry that illustrates the 3 to 4 bridge. Now I want to have a look at the same kind of picture, but from the point of view of Cartesian geometry. Okay? Cartesian geometry is geometry built up from coordinates, where we have an x-axis and a y-axis, and we have So a number line labeled here on the x-axis, say 0 there, 1, 2, 3, minus 1, minus 2, and so on. And similarly in the y-axis, say 1, 2, 3, or minus 1, minus 2, minus 3. This allows us then to capture the position of a point with a pair of numbers, okay, the affine coordinates of the point. So for example, this one here is the point 2, 3. Means it's over 2 in the x direction and up 3 in the y direction. So the x comes first, followed by the y. And the idea is to get this point here, go over 2 and then draw a line parallel to the y-axis through there, and go up 3 here, and then a line parallel to the x-axis through there, and where those two lines then meet is the point. So I'm starting now with 4 points, also a quadrangle, and they're labeled 1, 2, 3, 4, and here they are. There's 1 right there, 2 there, 3 there, and 4 there. And then here are the coordinates of these 4 points in this coordinate system. So the point 1 is sometimes called the origin. That's the simplest point with coordinates 0, 0, because it's where the axes meet. The point 2, which is down here, x coordinate is 1, the y coordinate is 0, so it's 1, 0. The point 3, the x coordinate is 0, the y coordinate is 1, that's 0, 1. And 4, we've already seen, that's 2, 3. Okay, now we can sort of do the same thing that we did before. We can draw the 6 lines determined by those 4 points. So there's 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. Those are the 6 lines. And then those lines meet in these 3 new diagonal points, A, B, and C. So A is where 1, 2, and 3, 4 meet. 1, 2, and 3, 4. So there's A right there. And that turns out to be minus 1, 0. So it's minus 1 in the x direction and 0 in the y direction. B, where 1, 3, and 2, 4 meet, is this point down here. And that's got coordinates 0, minus 3. And then a little bit more subtle, point C, which is right here, is where 1, 4, and 2, 3 meet. And that turns out to be the point with x coordinate 2/5 and y coordinate 3/5. So you might like to check these values. And you could do that in a number of ways. The simplest way is to get yourself a piece of graph paper. Okay, and if you have some graph paper around, I urge you to do this. To get the graph paper out, sort of reproduce this diagram and actually draw these lines and verify actually physically that the points of intersection are where I say they are. Another way of verifying it is to sort of try to understand, why that is. So for example, let's say this point here, why is that at minus 1? Why is that reasonable? Well, to go from here to here, we go over 1 and up 1. Okay, if we go over 1 and up 1 and over 1 and up 1 again, then we're going over to 2 and up to 3. So actually we do get to 4. Right? So just going over 1 and up 1 gets us from here to here, and then that same direction gets us from here to here. So that's convincing us that these 3 points are actually collinear, telling us really that this really is the meet of this line and this line. Of course, you can also calculate meets if you know a little bit of high school algebra, but this is very elementary, so maybe you don't even know how to do that. That's all right. So I just want you to verify, to get familiar with this way of representing points, and to appreciate that this is really the same diagram as I showed you in the previous diagram, but now it's in the context of Cartesian geometry, which is based on this coordinate framework. Now in Cartesian geometry, we want to describe points very precisely, but also lines very precisely. Lines are a little bit more complicated than points. So in affine geometry, which is what we're doing here, affine geometry sort of means a geometry which is based on parallels. Okay? It's also the geometry of so-called linear algebra. Pretty well the same thing. Okay, so in affine geometry, a line is described by a linear equation in x and y. I should put an x there, so those are our coordinates, x and y. And the form of the linear equation is a plus bx plus cy equals 0, where a, b, and c are some numbers, possibly negative or positive, possibly 0. But actually, b and c cannot both be 0. Okay, you're not allowed to have both of these 0 because then that's a kind of a degenerate case that doesn't really correspond to a line. So let me illustrate that kind of equation in its role by showing you the equations of some of the lines, in fact all of the lines, that are generated by these 4 points. So these are like the edges. Okay, so 1, 2, that's that line there. That's just the x-axis. And its equation is y equals 0, because that's the defining property of every point on here. So that point there is the point 3, 0. It satisfies the equation y equals 0. This is minus 2, 0. It satisfies the equation that the y coordinate is 0. In a similar way, this is the y-axis, and it has equation x equals 0. Okay, so what about 1, 4? That's that line there. It's a line that goes through the origin. It has equation 3x minus 2y equals 0. And let's just check that this point 4 actually lies on that line. Remember what the point 4 was? It was the point whose coordinates were 2, 3. So the x-coordinate is 2, the y-coordinate is 3. And if you plug x equals 2 in here and y equals 3 in here, yes, the equation is satisfied. So that's the condition for a point to lie on a line. The line 2, 3, it has equation 1 minus x minus y equals 0. And 2, 4 has equation 3 minus 3x plus y equals 0. 3, 4, this one here, has equation 1 plus x minus y equals 0. So having linear equations for lines is very powerful because it's easy to check whether a point lies on the line or not. You just substitute it in and see if you do actually get 0 or not. And a single equation like this will capture all the points which are lying on it. So it's quite a beautiful thing. So as a great exercise, especially if you're not too familiar with this or it's been a while since you've learned about lines, please check these equations. Okay, make sure that I've got them right. Make sure that this line really does pass through the point labeled 2 and the point labeled 4. Okay. Now, points and lines have been studied for thousands of years. But the ancient Greeks were also interested in sort of the next step up, which are more interesting, more subtle curves called conic sections, or just conics. And in the 17th century, with the work of Descartes and Fermat and the introduction of Cartesian geometry, it was appreciated that Apollonius and Archimedes and the other ancient Greek mathematicians, their study of these conics could be simplified in lots of ways by going to equations for the conics in this sort of Cartesian coordinate framework that we've just been talking about. So I want to tell you about that. So in affine geometry, a conic is described by a quadratic equation in x and y, quadratic of degree 2. So it has this general form: a plus bx plus cy plus dx squared plus fxy plus gy squared equals 0. You might wonder why I don't use e. That's because my computer system easily gets e confused with the special real number e, and so that's a bit problematic. I should also say that there's a slight caveat. In order to get a conic, we do actually officially require that one of these quadratic terms really is non-zero, so that d, f, and g cannot all be 0. One or two of them can be, but not all three of them. Okay, so that's then a conic. Now, the simplest examples of conics are perhaps not what you would think. You might think, well, it's a circle or a parabola. Actually, no. The simplest conics are actually products of lines. Okay, and we're going to introduce some notation for that. We'll say that a product of line is just a line pair. Okay, so we're going to introduce this terminology for these simplest kinds of conics. Sometimes they're called degenerate conics and maybe not even considered, but we're going to consider them. Okay, so let me give you an example. So back to the same configuration that I already showed you. Our 4 points here in the Cartesian plane, point 1, point 2, point 3, and point 4. I've shown you 2 of the edges, 1, 4, and 2, 3. Okay, now 1, 4 had equation 3x minus 2y equals 0, and 2, 3 had equation 1 minus x minus y equals 0. So the way we can get a conic from these 2 lines is to just take the 2 equations of the lines and essentially multiply them together. So we form a composite equation by taking 3x minus 2y times 1 minus x minus y equals 0. Now, a moment's thought shows that, since a product of 2 numbers is 0, implies that either the first or the second is 0, or possibly both. The points which satisfy this equation are just going to be the points which lie either on the first line and or on the second line. So in other words, a picture of this conic is just this picture consisting of these 2 lines. You might say the union of the 2 lines, but it's just, that's the picture. Now we could expand this out. We don't need to keep it in factored form. If we expand it all out using algebra, good practice for you if you're not familiar with this, make sure you can expand this out and check that you get 3x minus 2y minus 3x squared minus xy plus 2y squared equals 0. So that's the equation of a conic because it has this general form. And the degree 2 terms are not all with coefficient 0. But it's a degenerate conic, or we prefer to say it's a line pair because it actually can be factored as the product of these 2 linear factors. So it's actually a very special kind of conic. So now we get a nice additional correspondence between quadrangles and 3 things, namely between a quadrangle and 3 line pairs. So we've already seen that the 3-4 bridge is associating to a quadrangle 3 4 cycles, as well as 3 meets, and now we have something else, 3 line pairs. So let's illustrate that with the example that I already have shown you, where we have these 4 points in the Cartesian plane. This is the one I've already just shown you, where we have this product of lines, the line 1, 4 and 2, 3, and when we expand that out, we get this one here. So we've already seen this one, and this really corresponds to the meet 1, 4, 2, 3. Corresponding, let's say over here, 1, 3, 2, 4. So there's 1, 3, there's 2, 4. The equation of 1, 3 is x equals 0. The equation of 2, 4 is 3 minus 3x plus y equals 0. We put them together, we multiply them together, we get the equation 3x minus 3x squared plus xy equals 0. That's then the equation of the line pair consisting of these 2 lines. And similarly, 1, 2, 1, 2, and 3, 4. The 1, 2 is the x-axis that has equation y equals 0. This one here has equation 1 plus x minus y equals 0. We put them together, we get that thing there. We expand it out, we get y plus xy minus y squared equals 0. So these 3 conics are all line pairs, and they correspond exactly to the 3 meets of these 4 points. So if we go back to our earlier picture, we would have said, oh, this is the meet 1, 2, 3, 4. That's representing the point which is the meet of these 2 lines, or 2 edges. Yeah? Over here, 1, 3, 2, 4, that corresponds to this point down here. And 1, 4.23, that corresponds to this point here. Now we're introducing some variance to that, where we can interpret an expression like this, not just in terms of a point, but actually in terms of a conic. Admittedly, a conic of a rather special kind. Okay, as a bit of an exercise for you, especially if you have a little bit more algebraic facility, show that there is actually a linear relation between these 3 conics. What does that mean? It means that, I can, maybe if I take this equation and I take this equation and I add twice that equation, then I'm going to get 0. Something like that. Okay. All right, so that's great. So we've ventured a little bit into some geometry associated to our study of these combinatorial objects. I've introduced you to some very simple projective geometry and some very simple Cartesian geometry, and we've sort of reminded you hopefully of the equations of points and lines, and actually also conics in Cartesian geometry, illustrating the richness of the 3-4 bridge. I'm Norman Wahlberger. Thanks for listening.